Thank you very much. Beautiful talk. I'm sure there will be some questions. Just raise your hand. Okay, I see David Shivak. You have a question?
I think my colleague Tom was first. Tom?
I think you.
Am I muted?
Go first.
Yeah, thanks for the fascinating talk. Do I understand when you said define the yield? Did you say that was a ratio of carbon used in one thing to the overall carbon source or something like that?
Yeah, so exactly so you can define it in gram per gram. So for example, you can say how many grams of my bacteria do I get per gram of glucose consumed, for example. But what we usually try to do is to define this in the amount of carbon moles of biomass.
Right. But it seemed at some point that you were kind of saying this was equivalent to a growth rate. Is it equivalent to a growth rate, or is it?
No, it's kind of like equivalent to kind of like a growth efficiency in a way. So like the growth rate and the yield are not correlated at all. So you can have, so at least in our data set, it's not correlated. So right now, because of the nature of the data we're using, we really use Loos the information of time at the moment.
Okay.
So
it really is more dissipation equals more efficient use of your carbon resources in terms of incorporating it into your growing organism.
So at one point, right, like for the oxidative growth, yes, they are the most yieldful, but they're also the most dissipative one. And they have the highest, in our definition of thermodynamic efficiency, the highest efficiency. Exactly.
Okay. And efficiency, when you say 50% efficient, I mean, presumably you don't, or do you mean this, that of all the food molecules they're taking in and turning over, like free energy turnover of those fuel molecules, half of that free energy is going into building stuff?
No,
does it mean something else?
It does mean something else. So if you look at like how much, if you look at the overall dissipation and how much of the free energy actually goes into biomass itself, it's very neglectable. So what we empirically find is this opposing force which you need to overcome. That doesn't necessarily think about now. Like activation energy is the wrong thing to think of, but this is the opposing force you need to at least have, and then you need to dissipate a little bit more in order to drive the whole system.
So the 50% means that you're twice as high as the opposing force.
Exactly. So think about your classical myosin dragging something where you have your velocity and your drag force, which you need to overcome by the hydrolysis of ATP, right? Your classical free energy coupling and myosin transport.
Thank you.
Okay, David, now.
Okay, great talk. I guess I was curious about the violations of the second law, your examples that you mentioned, 1%. I guess, do they violate it by a little or by a lot? And does that give you sort of a feeling of like the uncertainty you should attach to any of your data as that kind of, they can't violate the second law?
Yeah, so these are usually data points where, so they don't violate it by a lot. So it's a little bit, but the free energy change is positive. But, if we give, based on the data, if we, include another molecule which they may have missed, they would then obey the second law. So, and you can already see the spread of the data is quite, yes, it's 500 and something, but the interquartile range is about 200. So there is quite a spread in the data, and we don't want to overemphasize the exact amount of that dissipation. There is some wiggle room around it, and this is of course depends on how good the data is. Right now, we can, experimentally we can do it much better, but of course we don't have the amount of data which you can achieve from that.
There's nothing to worry about yet.
Yeah.
Okay, so one final quick question from Vladimir.
Okay, good evening from Manila. And
Hi.
I would just want to go back to your slide comparing the engine and the one at the start, the engines and the
Oh, this one. Okay. Am I still sharing? Yeah, right.
yes, that
Sure.
one, yes.
Okay.
My question is well, this will sound really stupid, but at which what are the or rather what are the conditions for our biological setups to approach the Carnot limit of the Carnot limit of efficiency?
Short answer is I do not know. Right. Right now, it looks like the efficiency is below the Carnot limit, right?
Okay.
But I do not know to what extent this even applies, right? This is like all our data is very empirically, and at one point we have to see, right? And at one point we do not know whether there's any linear relationship between the fluxes and the forces so far away from equilibrium. We're still very at the beginning to start to see what is really going on. It's just not a nice approach in order to calculate the dissipation of on a macro scale. And now the whole fun starts to now can we design experiments to measure it and exactly look at these different properties far away from equilibrium.
Okay, thank you very much,
Okay.
Jonathan,
Thank
for
you.
this wonderful talk. And we move on to our next speaker, who is Sarah Loos. So I think last time we met, which was just last month, you were still in Cambridge, but I guess you're now in Göttingen. You're muted still.
Yes, sorry. Okay. Yeah, hi. Yeah, that's correct. I'm now in Göttingen. Can you see my slides
Yes,
well?
we can see your slides. And yeah, it will be a pleasure hearing you talk about optimal work protocols.
Yeah, thank you very much, Patrick. Thank you very much to the organizers for inviting me. It's a great pleasure to speak at this nice workshop in this nice session. Yeah, so indeed, I'm a postdoc in Cambridge, and I'm now in the transition period to go to the Max Planck Institute for Dynamics and Self-Organization in Göttingen, where I'm starting my group. And before I continue, I want to first thank my collaborators with whom I'm working on these topics of optimal control. And that is in particular the group of Clemens Bechinger, who are conducting nice experiments that I will also show later. And I want to particularly highlight the contribution by Samuel Monta, who is a PhD student in the lab who did all of the experiments that I'm showing. And my theory collaborators in the UK. So I've continued working on this with Mike Cates, Rosalba Garcia Milan, and Yannick Schüttler. And Yannick is also going to give a talk later today about a related topic. Okay, so as you all know, the framework of stochastic thermodynamics provides us with tools to quantify the efficiency of biological and synthetic processes at the microscale. And in the last talk, we heard a lot about these biological processes, which are really complicated and quite fascinating. And I think by studying optimal solutions, we can also tackle some relevant fundamental questions in different applications. So if we're thinking about biological processes, if we study on a theoretical level, thermodynamically optimized processes, we can see whether evolution has led to energy optimized solutions or not. And from an engineering perspective, if we were, for example, thinking about these fictitious micro robots here, which would be very useful to do a lot of tasks for us in the medical realm, it provides us with answers to the question whether it is possible to operate a certain machine with a given limited energy source. Now, if you think about such processes at the microscale, there are particularly important challenges. One is, of course, the presence of noise, which can be thermal or non-thermal. Another thing is that at these scales, due to the low Reynolds numbers, we have high friction, meaning high losses if we move things from A to B. So that also gives a motivation to optimize processes for their efficiency. And another thing that is maybe not quite as much recognized in the literature is the presence of memory due to slow degrees of freedom. that participate in the dynamics but are not directly controllable or measurable, giving rise to non-Markovian dynamics. And such memory can come from various sources. So if I think about these machines here, they can, for example, have internal degrees of freedom that operate on similar timescales, and that could give rise to memory. And another omnipresent thing is that oftentimes, in particular in biology, we actually have a coupling to complex fluids. So not just the viscous fluids that we like to use in idealized model systems, but viscoelastic fluids. This is true, for example, for blood, plasma, or the cytoskeleton. And this can give rise to significant memory effects in our dynamics. So having these memory effects can give rise to quite intricate thermodynamic processes. And I would like to give this little example here just to showcase this. So if I'm thinking of a particle that is dragged through a viscous fluid, the energy flow in the system has a quite linear structure. So we apply some external work to the process. Then this work can excite the internal states of the system, so increase the potential energy. But ultimately, this will be transferred to the bath in the form of heat. Now, if we think about this process in the presence of such a viscoelastic fluid, then the situation is a bit more complicated. So these additional degrees of freedom can serve as a transient energy storage because they can store elastic energy, if you like. So in this case, for example, this fluid has this microstructure that is similar to a net or an elastic network. And if you move the particle through it, you actually distort this network. And that's like charging a spring. And so this energy can be transferred back to the particle, at least partially. However, the energy can also be dissipated to the heat bath immediately. And that kind of energy is then, of course, lost for our process. So if you want to optimize things, you would ideally want to optimize the amount of energy that you lose. And we can actually see this energy backflow quite easily in experiments. So here you see a so-called recoil experiment where a particle, or in this case, actually it's a trimer of 3 colloidal particles, is trapped in an optical tweezers. And the tweezers are dragged for a certain time. And then at the end, the trap is simply switched off. If you had a viscous fluid, the particle would just come to a rest at the, up to fluctuations at the position where you stopped the trap, where you switched off the trap. If you had a particle with inertia, you would continue a little bit in the direction of dragging. But instead, if you now have a particle in the presence of such a viscoelastic fluid, what happens is that the particle is actually moving back in the opposite to the direction of the dragging. And that is called the recoil. And this is just a simple example to show that this energy flow is transferred back to the system, at least partially. And now if you want to optimize processes that have these memory properties, you would ideally like to recover this energy as much as possible. So I'm interested in the question how such thermodynamic processes look like if you have memory, and how optimal solutions look like. As a side note, there are some fundamental problems associated with having memory and doing thermodynamics. So first of all, what's kind of the dynamical description of such a system? Because we're thinking about continuous processes, we use a generalized Langevin equation, which is suitable to describe such a colloid in a viscoelastic system, where you have retarded friction and a colored noise, both introducing memory. If we are in equilibrium, we know that they are related, but that doesn't have to be the case. Now, from a mathematical point of view, as a side note, the dimensionality of the system is now given by the spectrum of the friction kernel or memory kernel. And in general, that can be infinite dimensional, which is already an indication that it can be quite tricky to solve these problems in general. And now if we're thinking about thermodynamics, there are 2 fundamental issues, if you like. So first of all, if you compute the entropy production per se, per construction, you will not be able to recover the full amount of entropy production because in your model or on your level of observation, there are just degrees of freedom that are missing, and you can't have any idea how much entropy you're missing. But of course, you can find lower bounds. For example, we generically know that the coarse-grained entropy reduction should be lower bounds to the full entropy reduction. Another interesting thing is that the backward process in such non-Markovian processes is actually acausal. And that's because if you reverse time, then the memory will, then you will have a process that depends on its own future, which is an acausal process. You can still write down a generalized second law if you want to, and incorporate information theoretical terms to account for this information flow between present and past. This has been done in several papers, in particular by Martin Rosenberg and his collaborators, and I think Martin is also here. But we don't have to deal with this problem here because we are only looking at work, and the work is not really affected by these issues. So I'm thinking about a thermodynamic optimal process. So I'm asking, I have a system in state A, I want to transfer it to state B in a given finite time. And the question is, what is the protocol to bring me from A to B such that the process is optimized from a thermodynamic perspective? And that can be framed in the language of optimal control problems, where now the cost functional is a thermodynamic quantity such as work, heat, or entropy reduction. And as I said, I'm going to focus on work for the reasons that I just named. And just in general, A and B do not have to be two locations in space, in real space, but there could also be two conformations of a macromolecule, or there could be an order parameter, say, of a many-body system, as it has been done in these nice papers here on optimal control. Of course, we are by far not the first people to think about thermodynamically optimal control. Actually, there are many people in the audience who have worked on that already for a long time. So I just want to mention a few things that are well established in the literature. So first of all, for linear systems that are Gaussian, these problems can be solved analytically, as has been done in this seminal paper by Tim Schmiel and Udo Seifert in 2007 already. For example, for this trap stiffening problem here. And what they showed is that there are discontinuities at the beginning and end of the process. So the optimal way of stiffening the trap with a particle inside is actually to quench rapidly, then you go slowly, and then you quench rapidly again. And these so-called bang-bang solutions are quite omnipresent. Later in the group of David, it has actually been shown that these are generic for fast protocols. So if the control time is very short, you would always have these jumps. And if we go away from such analytically solvable problems, then there's also a couple of approximative schemes available in the literature, also, for example, by David, which allow us to go to nonlinear problems. However, for the problem that I'm going to discuss now, we do not need to use them because we can actually solve it again analytically. Okay, so what is the problem that I'm now going to present? We were inspired here by these, for example, molecular motor that transports a load from A to B. But this is, of course, way too complicated. We want to have a minimal model that we can solve analytically. So we are thinking about a simple carrier that is harmonically connected to a load. And the task is now to transport the carrier from A to B in a finite time such that the overall work is minimized. And this problem is equivalent to having a particle in a trap. And that is very nice because this is something we can realize easily in experiments of colloids trapped by optical tweezers, as done by my collaborators in Constance. And this problem has also already been tackled in this seminal paper from 2007 that I already mentioned. And the nice thing is this is a minimal setup, which is simple enough so we can study it analytically and investigate the impact of having memory. Okay, so what is the work? Why do we have to apply work to drag the particle? Of course, if we move the trap, then we increase the potential energy of the particle in the trap, and therefore we have to supply work from outside. So the work functional is given here as the simple form. It is quadratic in the protocol and linear in the particle position if I write it in this form. And now let's start with the viscous case, which had already been solved in 2007. And so we can describe the particle dynamics by a Langevin equation that is Markovian in this case, if we just have a viscous fluid, which has one parameter that is a trap relaxation timescale. And this is a linear problem, so we can solve it exactly by Euler-Lagrange equations. One just has to be a bit careful with the boundary constraints, but it's quite straightforward. And what you find is the protocol shown here. So this is the trap center as a function of time. And as you see, again, the optimal solution has these characteristic jumps. So the optimal way of transporting is first quenching the trap, moving it really fast, then go slowly over time, and then moving fast again at the end. And if we allow for mole control time, we see that these jumps get smaller and smaller over time, and eventually they disappear in the quasi-static limit, as I'm showing here in these three plots. And here I'm showing the protocol, and I'm also showing the mean particle position at the same time. And I think this already gives us an insight why we want to do this first jump. Namely, by doing the first jump, we quench the system immediately into a situation where we are in a non-equilibrium steady state. So the distance between trap and particle, mean particle position is constant over time. And that's the most energy efficient way of moving through the fluid. Okay, so this was already known, but it hadn't been realized in experiments. So there, my collaborators and Constance came into play. As I said, they have a particle in a trap. Instead of moving the trap, what they actually do is they actually displace the fluid cell, which is easier to do, so they don't have to deal with the calibration, the change calibration of the laser. And thereby they can now realize different protocols and measure how much work they applied for each of these protocols. And what we did was we said, okay, the protocols all have the same form with a jump and then a linear dragging in the middle, but let's vary the jump height and measure the work and see what comes out. And here on the right-hand side in this plot, you see by black symbols the work. And as you can see, there is a pronounced minimum, and the minimum is in the region where the optimal jump height is, which tells us that, yeah, the theory is confirmed and these experiments match really nice to the theoretical prediction. And this is without a fitting parameter because we can measure the viscosity and the friction by individual equilibrium measurements. So we don't have to fit anything here. Okay, now let's switch to the non-Markovian problem. We add these viscoelastic fluids. And in this case, they use swarm-like micellar solutions or polymer solutions. And now we use the generalized Langevin equation. And the good thing is that these systems are simple enough such that the memory can be described by one or two exponentially relaxation memory kernels. And that means that I can rewrite the generalized Langevin equation in the form of n-coupled Markovian equations with these auxiliary variables. Each of them represents one timescale in my process. And that allows me to solve the problem in principle in the same way as before. So I transform to this extended Markovian system, and then I can do the Euler-Lagrange there, and then I can project back. And I'm just showing this to show you that although this is linear and very kind of a simple looking equation, the optimal protocol and solutions that we get are already quite nonlinear and complicated in this simple case. So this was the Markovian solution. So now let us look at the non-Markovian solution. So in the non-Markovian case, we still have the jumps at the beginning and at the end, but in between there is no linear dragging regime anymore. And I think we can understand that if we are thinking about this elastic energy reservoir that we have, which kind of forbids us to, I mean, it's not the optimal way anymore to just go linearly in time, because then at the end we would have this recoil. So instead we want to move in a way that we put as little energy into this elastic energy storage as possible. And again, we conducted experiments confirming our optimal solutions from the theoretical prediction. Then my experimental collaborators noted something peculiar about all the optimal solutions that we looked at. And that is the following. So if we look at the overall process, it is not time reversal symmetric, because at the end, we're actually not in equilibrium and there's going to be a relaxation afterwards. However, if we just focus on the time during which we conduct the control, so from time 0 to TF, both the particle trajectory as well as the protocol obey this time reversal symmetry property. And they asked me, why is this the case? And this is not only true for the viscose, but it's also true for the viscoelastic solution. So I looked into that, and I first thought that there should be a thermodynamic reason for this time reversal symmetry, but I couldn't find any. However, I could find mathematical reason. And I want to show you a little bit a little bit the mathematical insight that we found from this consideration. So if we're thinking about the symmetry of the protocol, the symmetry of the mean particle trajectory, and the question of optimality, there are a lot of possible implications and non-implications. And as I'm showing here in this diagram, this is what we could prove. And we could prove these implications for a generalized Langevin equation by using the linearity of this generalized Langevin equation, causality, and time translation invariance of the response function and memory kernel. So it does hold for a very big class of systems. And I don't want to go through the proof. Also, I'm a little bit behind in time, but I just want to give you the main idea. So the main idea to prove that is to rewrite the mean work as a functional of only the protocol or only the mean particle trajectory, which here, for example, can be done by using just the response function formalism. And then you see that if you write the mean work as a functional of only the protocol, for example, it's a quadratic protocol in lambda dot. And that has immediate implications. So first of all, because it's quadratic, it's invariant under time reversal. So for any protocol, the work of that protocol and the time reversed image of that protocol are identical. But because it's quadratic functional, it can only have one unique optimum. And that means that the optimal solution itself needs to obey time reversal symmetry property. And now we can also write the work functional as a functional of only x dot. And then again, it has the same quadratic structure. So the same argument holds for that. Now, finally, to complete this proof, you also need to show the reverse direction, which you can do by assuming that you have these symmetry properties of lambda and x, and then you can show that by using the generalized Langevin equation that you always have this integral equation here, which then, on the other hand, is equivalent to having zero variation of your work, meaning that your process is optimal. So in total, when we complete all these steps, what we have is that the symmetry is a unique property of optimal solutions, and it goes both ways. So every optimal solution needs to obey the symmetry properties, and every symmetric solution with these properties is optimal. And I think this is quite strong, because that means, for example, that you can use the asymmetry as an alternative cost functional. So instead of minimizing work, you can minimize asymmetry, which is a better cost functional in some sense, because you know the value at the minimum a priori, which you don't know for the work. So you know if it's completely symmetric, you have to be optimal. If you optimize for work, you never know if you have quite reached the global minimum. And we have demonstrated that by training a machine learning network, a deep neural network, to optimize for symmetry instead of optimizing for work. And in both cases, they find the same solution, just to make a proof of concept. And the other important thing is that in our proof, we didn't use any particular properties of the memory kernel or the colored noise. We also didn't use FDR. So this property should now hold for a large class of systems, including particles in granular or glassy media and active particles as well. Okay, as an outlook, to go to more complex situations, we are now employing an approach where we couple a Langevin equation to a field theoretical equation so that we can model much more complex surroundings, such as, for example, fluids that are close to a critical point. For the steady state driving, we've already demonstrated this in this paper here in 2024. And now the question is, how do optimal finite time solutions look like? And finally, I just want to mention again that we are now studying also this problem in the presence of active particles. And Yannick is going to tell you more about that later. Okay, with this, I want to just wrap up and thank you very much for your attention. And I'm happy to take questions if you have any.